Okay, welcome back. Here's another video here, continuing on with the intro to, I think it's probably the third video for the introduction to exponents here. And we can go back and review if you want the summary. You can pause the video or watch the beginning of the last one. But pretty much as a summary, we ended up talking about, again, that we have an exponential function if you have an initial value, a growth factor or a decay factor raised to some power for the input. Remember, this is the input, usually time in our cases, and this is going to be the output with a dependent variable. So we've talked a lot about that, and also kind of added on to it that if b is greater than 1 or 100%, it's going to be increasing. And if b is less than 1, it's going to be decreasing. Now I bring all this up in summary because our next few questions are going to have a lot to do with this growth or decay factor, or the constant multiple. All right, remember, I've said it almost every video, linear functions have a constant average rate of change, meaning slope. Exponential functions have a constant multiple, or a growth or decay factor, whichever way you feel comfortable talking about them. So going forward, for instance, you're going to have, and these didn't come out, but this is 5 to the 3/4 x, and that's going to be f of x. And the question is going to become, is this function increasing or decreasing? Now, if we put this into a calculator, and we'll get practice with that later, or maybe even now, but that's 5 as my stylus kind of, or 0.75 to the x. Now here, b is less than 1, so it's going to be decreasing. And you could do this for every one of these examples. I won't, just for time's sake here, but if you went back to a calculator, and again, that's problems from last example, but if you did 5, I think it was 5 times 0.75 to the x power in a standard viewing window, in other words, 6 by 6, that function, that's what a decreasing function looks like. Now remember, a decreasing function, since we've not really talked too much about it quite yet, at least on these videos, is going to have a horizontal asymptote here. Again, it's written like this. Excuse me. So a horizontal asymptote, that's how it's written. And it's really like an invisible boundary that your graph, at least the blue function here, is going to approach infinitely close, but just can't ever quite get there. So your y value in this case, unless you're messing with the function, will always be greater than 0. But it's decreasing. Notice the y's get closer and closer to 0, but can't get there even as you're going this way. Okay? So let's go back to our problems now, because only really the real question was, is your function increasing or decreasing? So the answer to the first one here was this one's decreasing. And I apologize for the formatting. I don't know why it's doing what it's doing. And for the second one, g of x was supposed to be 5 times 4/3 to the power of x. Now really that's 1.333, I think. That's over 1. So because b is greater than 1, it's increasing. And again, you will get a graph that's increasing from left to right, again with an asymptote here at y equals 0. So just remember this summary in green. Initial value, it's increasing or decreasing by a constant multiple or a constant percent change. And you always have, again, I'll revert back to this rate at which it's increasing or decreasing, which we'll keep talking about as we get more familiar. Now, I should say something, people's ears perk up usually. This function is what dominates my life and probably will dominate just about everyone's on the planet, unless you're, I don't know, they have those shows that where you're roughing it up in Alaska off the grid, but this function here dominates your credit card bills. It runs your house bills. If you have a house loan, if you have a car payment, if you have a student loan, it applies to everything that requires there to be a constant multiple or stuff like an annual percentage rate over time. So anything that multiplies at a constant percent change is going to be dealing with this kind of exponential function. So, but before we get there, let's practice on kind of identifying what's exponential and what's not. So if we're looking at linear functions, linear in red, f of x is a linear function. 5x, 5 is the slope, 6 is the y-intercept, minus 6. Even if it's written backwards, so we'll put an L here, h of x here is linear. It's just written backwards. So instead of y equals mx plus b, and this should just be review at this point, y is going to equal b plus mx. And the slope in this case is negative 7, and the slope in this case is 5. The y-intercept in this case is negative 6, and the y-intercept in this case is 2. Okay, so what I want you to do, here I'll do 2 more for you. In blue, this is exponential, and this function here is exponential. So this function is exponential with an initial value of 4 and a growth factor that is increasing, well, that is 3. So that growth factor is increasing because it's bigger than 1. And hopefully you should be able to do this one. This is exponential with an initial value of 8 and a decay factor of 1/2. All right. So going forward, the question should be, hopefully, like I just did the first 4 for you, and even for this last one, I of x over here, if I asked you, okay, the initial value is 8, you got that, decay factor was 1/2, but if I ask you by what rate is it decreasing, remember b is equal to 1 plus a r. So in this case, my growth factor is 1/2. Watch what happens. Now you might be able to see it, but if you can't, if you go ahead and solve for your r, oops, it's decreasing by 50%. So in other words, if you started out with 8 and you took half of that, after one iteration, you probably have 4. So the rate of decrease, you would say it's decreasing or going down. I don't care if you put the minus sign there or not, but it's either going down or decreasing by 50%. So that's the third thing that's not being asked that I'm going to be asking you going forward here. So get used to that. Okay. All right. So pause the video. Do the next 4: J, K, L, and M, because that's what's going to be asked for your lab and your homework. Okay. Pause the video. Come on back. I'll help you out, and I'll wait for you. Okay. If you're back, if I asked you which function's linear, you should tell me, and I'm going to do this verbally so I have some room here, m of x is the only linear function. And if I said, how come? You should tell me because it has a constant average rate of change. The m is 0.5x, and the b, or the y-intercept, is 8.2. So hopefully you're taking the time to really get acclimated with the exponential function in general. Now all of these other 3, J, K, and L, are exponential. So if I ask you what is the initial value for each one of them, and I won't write this time, initial value is here in black. So it's 0.5 for that function, 5 and 5 here. They're the same value. Those are also, so they're the initial values in black, and that's also the y-intercepts. So where your function will, if you were to graph these things, where it crossed the y-axis. J of x has a growth factor of 1.6. And if I ask you, it's 1.6, so it's increasing because it's over 1, right? And if I ask you for the rate of increase, if you can't see it, just calculate it off to the side. So here's 1.6 minus 1 minus 1. So 0.6 or 60%. Remember, I kicked that decimal to the right 2 spots if I want to talk about it. Oh, 60% rate of increase. Okay. For k of x, that's this one. let's do a different color. We'll do it in blue. K of x is exponential, and its decay factor is 3/4 or 0.75 if you do it on a calculator. 0.75. If I ask you for the rate of decrease, -1, -1. And again, I'm always coming up with this b is equal to 1 plus a r. And you saw me just kind of write it intuitively. I just kind of forget the b and I just, put the 3/4 there. And this is going to be negative 0.25 equals r, or 25% decrease. Okay? Sorry for the sloppy notes. And the last one, if I said, what's the rate of increase or decrease, you'd say my decay factor. Excuse me. It's not the decay factor. This was just like it's the exact one from the last example, example 2. It's, gosh, I blanked out. The growth factor is 4/3 or equal to 1.3. Sorry for the stylist again. And if I did 1 point, I can't get away with that. Sorry. Let me rewrite that. So the growth factor, 1.33, and 1.33 equals 1 plus a b minus 1 minus 1. And again, you might be able to see some of this sometimes. So minus 1 minus 1. Oops. Sorry, now I'm going crazy. It's not me, it's just the pen. But notice my rate is still increasing by 30%. And you can put an arrow going up or a minus like we did here to increase. But every time you talk about the rate, you need to talk about the percentage and if it's going up or down. Okay? So the other examples you might see on the midterm, and I bring this up because you're going to see it, or the final exam, will be a bunch of tables. And I'll say which ones are linear, which ones are exponential. And depending on if it's linear or exponential, go ahead and get the equation for all 4. Now I'll do the first one, and I'm going to ask you to do the next 3, which I'll kind of go through pretty quickly. But so for this first one, in the table, what I'm looking for, I'm going to go ahead and test to see if it's linear first. If it's linear, then I should have the same y2 minus y1 over x2 minus x1. So watch, I'm going to test the slope. 6 minus 2 over 1 minus 0. And in this case, that's going to be 4 over 1, or just 4. And then I can test the next pair of points. 18 minus 6 over 2 minus 1. And that's going to give me 12 over 2, or 6. Now this is different than this. So that means it's not linear. And on an exam, I'll ask you if it's linear or not and how come. And in this case, it's not linear because not an average rate of change. A little triangle means change for me. Okay? So if it's not linear, and because we're just doing these kind of examples, sometimes it could be quadratic, and you've messed with those too. But in this case, it's not linear, so you're going to say this one's exponential by default, because there are only 2 choices right now. So if it's exponential, remember, y equals ab to the x. The initial value is just 2. And if you can tell, and here's how I always cheat. You can tell the multiple if you take one value, and let me erase this for a second. Remember, y equals ab to the x is the function we're looking for. So some power here. Now, my cheat way is as long as these are going in equal increments, and that's a huge if. As long as you're going from 0 to 1, 1 to 2, 2 to 3, 3 to 4, as long as you take one value and divide it by the preceding value, 6 divided by 2, it should equal the next 2, 18 divided by 6. What is 6 divided by 2? 3. 18 divided by 6 is 3. Try it again. 15 divided by, sorry, it's not coming out right in my pen, but 54 divided by 18 is also 3, and that'll be the truth for 162 divided by 54. That's how you find out your constant multiple for now. You're going to take as long as you're counting in the same amount of time forward, you can take one value and divide it by the preceding value, and that will give you your growth factor in this case of 3. Okay, pause the video and do those other 3 tables as fast as you can. And actually, I guess go ahead and take your time. There's no rush. Pause the video and come back and I'll kind of crank these all out for you. Okay, don't know how long that took, but if you're looking at this stuff, the second function here, and I'll do this one in gray, this one is going to be exponential, I think. And I'm looking at it, remember, 1 divided by the preceding one, 54 divided by 162, is going to be the same as 18 divided by 54, and 6 divided by 18, or 2 divided by 6. Do you see what I'm doing? Every time, 1 divided by the preceding one. Because I'm trying to find out that constant multiple, and in this case, the answer is 1/3. Now, if you have the constant multiple anywhere, that's a guaranteed exponential situation. So remember, I know it might seem like it's a broken record, but we had a constant multiple in black here. Constant multiple was 3. My constant multiple in this case is 1/3 for the second equation here, which is right here. Once you can find that it's a constant multiple, and you are more than welcome to see if there was a constant average rate of change, but there's not. Even if the first 2 or 3 values it's potentially they could be the same, which is why you got to check them all. But in this case, your initial value is just 162. My decay factor is 1/3 to the power, and that's my answer. Okay? And again, I'm not trying to cut corners, but just for time's sake, you need to do all the checks like we just did for each one of these problems. Meaning, in the black for the first problem here, we checked to see if it was linear, and because the slopes were different, it wasn't linear. We stated that, and so we said it was exponential. In this case, I've already gone ahead. I'm assuming you pause the videos. Same reasoning, not linear because there's not an average rate of change. Okay. For this next one, I don't know. I haven't done these pre-done them, but in my head on my calculator as I'm talking to you, I'm taking 99.5 and subtracting 120. That's minus 20.5. So, and then 79 and subtracting 99.5 minus 20.5, and 58.5 and subtracting 79. So here, notice what I'm testing already, and you can do the test very quickly. I'm not looking for a constant multiple. It just looks like 99.5 subtract 120 over 1, or 1 minus 0, is going to be the same as 79 subtract, I'm sorry for my pen, 99.5 over 2 minus 1. Those all equal, or what do we say, minus 20.5. That's the same average rate of change. Do you see the difference? This one before was a multiple, whereas this one now that we're talking about on the bottom left of the screen here, that's my slope. So as far as an equation, I'm going to have y equals negative 20.5x plus, remember, here's your formula, plus b, and you can rip your b off the table because you know that's your y-intercept right there. So there we go. Now, as we're talking about these, because I only got one more example and then these videos will be over, if I said, is that linear function increasing or decreasing, you could still say it's decreasing, but because there's a negative here in the slope, which means on a graph, your line, if you had one, would be coming down like this. Okay? If I said, what's the y-intercept, you should tell me 120. For the previous graph, sorry, motorcycle, up in blue here, 162 is the y-intercept. I guess they turned around and came right back. And 1/3 is the constant multiple. So you see the difference in language? Both functions have y-intercepts. This one's in red. The other one is in blue. But The difference in the two functions is that the average rate of change only applies for linear functions, whereas a constant multiple or constant percent change only applies for exponentials. So that's kind of the summary. Okay, last one here. I'm already looking at the difference here is 10. The difference here is 9. The difference here is even less. So I know there's not a constant average rate of change, no exponential, or excuse me, no linear, which forces the darn thing. Let's do a different color. Let's use, oh, I'd use highlighter to be funny, but oh, let's just use blue. And so I'm going to see right off the bat y equals ab to the x. And what's my constant multiple? So 90 divided by 100 should be the same as 81 divided by 90. And it should be the same as 72.9 divided by 81. And let me check here on my calculator, 72.9. Sorry, you can't see my calculations just for speed, but this should be 0.9. This is going to be 0.9. And I'm going to guess that this is 0.92. So that's my constant multiple. My initial value at time 0 is 100 times 0.90 to the x. And you're done. Again, this is the initial value. This is my growth factor. And then as a bonus question, just before the video ends here, if I ask you, at what is the rate is this function increasing or decreasing? All you need to do is revert to this. It'll be on your formula sheet and say, well, Mr. J, my B in this case is 0.90. Sometimes you can eyeball it too, like 90%, what's left? Or you can come over here and answer the same question. This means negative 0.10 equals my R, or it's a 10%. Now notice again, you could say decrease. That means going down, or minus 10%. It's the same answer, but you need the negative or the decrease when you're speaking about the rate of change. Excuse me, not the rate of change, but the percent increase or decrease. Notice my slipping words there. The average rate of change, only for linear functions. Constant percent change, only for exponentials. Got it? So that should be enough to get you through the lab homework, and just do as many word problems and many charts and tables and practice as you need to make sure you got all this stuff down. All right? Good job, and we'll talk to you later.